All right, hello and welcome to CSCI 26. I am excited to be here with you. First of all, the reason I'm not making my presentation full screen is because I get much cooler pens this way. So that's why, if it bothers you, sorry. Let's talk about what we're going to talk about. So we have that standard first lecture stuff to talk about first. I'll tell you about me. That's probably somewhat interesting to you. Then we'll talk about the class and the syllabus and all the requirements. That's probably extremely interesting to you, right? And then we'll actually get into some real CSCI 26 content towards the end because we cannot miss a day. All right, so that is the plan, and let us get started. So a little bit about me. Hello, my name is Lawton Nichols. I use he, him pronouns, and I will respond to, I don't know, Mr. Nichols, Dr. Nichols, Professor Nichols. But honestly, I'd prefer it if you just call me by my first name. Please call me Lawton. I would like that. Thank you. So, yeah, that's a little bit about me. If you want to see my face, please come to office hours. But I have a cat and some moss balls to show you on the side for now. All right, so I went to Fresno State for my undergrad. I got a computer science degree there. And then I went to UCSB, UC Santa Barbara, and got 2 degrees there. They're all in computer science, though, so hopefully I can teach you something. Other than being a teacher, I like to dance, I like to play guitar, I like to rock climb. Please talk to me about all those things. I would love to discuss. And then, yeah, here is my cat. He is named after Alonzo Church, so his name is Lonzo. Alonzo Church, maybe you've not heard of him, but I'm sure you've heard who he was the PhD advisor of, Alan Turing at Princeton. So, yes, I have dedicated my cat to computer science. And then I also have 2 moss balls that are unnamed, but they're pretty. Okay, so that's a little bit about me, and I think we were able to fit it all in a slide, so great. This is an interesting time that we live in. I think, what are we, post-pandemic? It's weird, so thank you in advance for putting up with me throughout this semester. We'll get through it together. So, all right, the moment you've all been waiting for. Let's go as fast as possible through this. You are responsible for reading the syllabus, of course, but let's talk about like the requirements and what's going on with the class so that we're all on the same page. Okay? So, first of all, this is an asynchronous class. I'm going to record everything. Every lecture, every lab. Sadly, it has to be this way because my Tuesday, Thursday schedule is full. We need this to be, we're going to pretend that this is a Tuesday, Thursday class, even though I don't have time in my actual schedule to make it a real one. If this were to be a Monday, Wednesday class, there would be too many holidays for all the content that we need to get across to you. So that's why it is like this. Please come to office hours. We can talk as much as you want in person there, okay? So, here is my schedule that I'll try to keep. We're going to pretend that this is a Tuesday, Thursday class. I'll have the first video up by Tuesday, sometime in the afternoon. Second video by Thursday, sometime in the afternoon. And then Fridays are going to be our lab days, the days that they're due, so I'll probably introduce them. I'm going to try to introduce them by then as well. Okay? So that's my plan. I'll try to stick to it as much as possible. This lecture, of course, is going to be out super early. I'm going to try to keep that schedule, but if nothing else, this is my latest due date for myself for all these things. Okay? Because it's asynchronous, because it's an online class, I can't expect you to be somewhere at a certain time, so I'm going to give you at least a 24-hour window for all the exams in the class. But once you click start, they'll be on Canvas. Once you click start, they're going to be timed. So they'll be like a 90-minute or an hour and 15 minutes for a midterm, something like that. Just plan for that, and that's how it'll be. So you'll get some time to take it whenever you can take it, all those exams and things like that. Okay? Let's talk about expectations. CSCI 41 is supposed to be the hardest class at the college, or I think maybe in the district. CSCI 41 is just weird. It's a lot of new stuff, right? So you survived that, and so it's technically all downhill from there. But this class is, I would say, a little difficult as well, okay? I can't say it's an easy class, 26, but I think it's slightly better than 41 in some areas, okay? One thing you got to watch out for is most of this class is concepts you have never seen before. they are brand new for a lot of us, okay? And maybe there are some things that we've seen before, but we're going way in depth. This is a math class, okay? It's weird to think about. This is really a math class, okay? And so we're going to be very, very formal, okay? And because of that formality, maybe the class, we should say it's more tedious than it is difficult. You're going to have to learn to speak in a way that is very, very precise, and that takes some time to get used to, okay? You're going to have to write a lot of proofs, so that's going to require you, first of all, to write if you don't like that, and then second of all, to speak in a way that maybe you're not used to speaking, okay? This class is, it's weird in that this is a computer science class that doesn't really involve labs a whole lot. Labs are going to be kind of like a second thought to us. What's really going to matter in this class as far as assignments are concerned are homework. So I'm going to give you written homeworks because I need you to do math problems, okay? And a lot of those are going to take time, okay? So I promise it's all worth it. I'm not asking you questions just for the sake of asking you questions. Once you get to a four-year college, you're going to use everything we learn in this class for the rest of your life. I promise. Okay? So yeah, that being said, this is going to take some time to do the work, okay, for this class. So expect to use the rule. Maybe you've never heard it before, but this is a 4-unit class, right? Which means you spend 4 hours in class, like watching videos, taking notes, stuff like that. And then you double that, and that's how many hours you're supposed to spend outside of class to do the work. Okay, so expect to hit that 8 hours outside of class rule some weeks. I'm warning you now, okay? But I'm really not trying to scare you away. I promise to help you as much as humanly possible. I'll be on Discord all the time. The tutorial center is here to help you as well. This is a hard class, but I promise that you can get through it if you put in the work. Okay, so that's expectations. I just wanted to be upfront with you about that. So yeah, let's get right on into it. Let's keep going through all the rest of this stuff. First of all, the college, if you need it, they will check you out laptops. They will check you out Wi-Fi little, I think they're called MiFi routers. So they allow you to get a faster internet connection if the one at your house is not as good. It's through like a cellular network. So if you need either of those things, check the resources page on Canvas. Very, very helpful stuff. Definitely take advantage of that. And let's go to the syllabus. All right, let's make it happen. So here's the home page for the course. Hopefully you went to the modules page by now. You got to click some stuff to unlock things. But the place that I'm going to take you now is the syllabus. So let's go there, look at that. Please yell at me if anything looks wrong. Maybe something still says like 2022 on it or something. I tried to go through it though. So here is our syllabus. Let me just summarize it for you here. The types of assignments you will see are mostly, the bulk of the work is going to come from homeworks and programming assignments, and then also some reading assignments. So the homework and the programming assignments, I'll call the programming assignments labs. Those will be assigned at least every couple weeks, most often every week though. So prepare for that. This, like I said, is a weird class in that it's kind of like a math class. So the homeworks, the written homeworks, matter much more than the labs, I would say. So I'm not giving you as many labs as I would in like a CSCI 41, CSCI 40 class, okay? So those are your kind of assignments. We'll go to the grade breakdown. This is probably the place you want to look. Please read everything else. But yeah, we got some written homeworks. You got some labs on the class server. Homeworks are worth much more than the labs. Okay. There'll also be some reading assignments from your textbook. Those check-in surveys that I'll use for attendance. That's 5% of your grade. And then there's going to be 2 midterms and a final. Okay. They're all going to be weighted the same. So yeah. 2 midterms, I'll try to make them be 2/3 of the way, or 1/3 of the way into the semester and 2/3 of the way into the semester, because then at the end, 3/3 is the final. So that's when I'm going to try to have the exams, week 6 and week 12 for our midterms. The grade breakdown I just showed you. Please read it. I think it's pretty standard. There's going to be extra credit. I like to give at least a letter grade's worth of extra credit if you need it, so take advantage of that. Usually around exam time, so I'll talk about extra credit. And yeah, check-in surveys are important for this online class because that's how I'm taking attendance, first of all, so I'm going to drop you if you don't do them. And then also, it's just an easy 5% of your grade. Just write something, tell me how you're feeling. I'm forcing you to psychoanalyze yourself, and you get a very, very easy half a letter grade of credit if you do them all. Okay? Let's also talk about the final, because this is a class without a time. So here is what I'm going to have the final exam. I'm going to make it available during at least a 24-hour period on the Monday and Tuesday of finals week. So that's the 15th and the 16th, okay, of finals week. So yeah, that's the plan. Please read everything else, but I think that's what you care about the most. So yeah, a lot of written homeworks. That's probably going to be the bulk of the work for the class. That's the most important stuff. That's the highest scored stuff, will be your written homeworks. Okay, so let me talk to you about how I'm going to grade them. So I will not be super harsh. I promise not to be super harsh when I grade your homeworks, because it's not a test, right? It's just you doing the homework. So here's my promise to you. If you get at least 70%, like a C, a low C on the homeworks, you get 70% of the questions correct, and you tried every problem, and I can tell that you tried, then I'm going to give you 100% on your homeworks. Okay? That's how it'll work. If you don't try them all, then I start taking off some points. Okay? So please just attempt every problem, and I will give you most likely 100%, unless you don't do them anywhere near close to correct. Please ask me if you're wondering about a question. It should not be too hard to get at least a 70%, okay? Especially if you ask me about stuff, all right? Also, a lot of people like to not type up their homeworks. They like to write their homeworks and scan them and then upload those to Canvas. If I can't read what you wrote, I unfortunately have to mark your answer incorrect. So please write nicely. I'm sorry that I have to say that in college, but it happens that I can't read some stuff. Okay, so that's homework grading. Let's also talk about due dates. I think you maybe have noticed with the check-in survey, it's due at what, 5:30 on Friday? So all assignments except for the check-in surveys, which will be due at 5:30, will be due at 5 p.m. Okay, so this is something that I like to do in my classes. I just want to tell you about it right now. This makes sure that when things go wrong, and things will go wrong because this is computer science, I'm awake and I can help you with technical difficulties, etc. All right, so that is why I do it this way. Please keep that in mind. All right, and that's going to be your due date for most assignments in this class, 5 p.m. All right. That being said, I do make some exceptions for certain kinds of students. So let me know if either of these apply to you. Make some equity exceptions, I call them. So if you work at least 20 hours per week, half time. School doesn't count. If you're taking 20 units, that's your fault, right? Some people have to work, though. If you work at least half time, I will extend your due dates an extra 7 hours, so your due date is now midnight for the assignments, okay, rather than 5 p.m. So let me know if that applies to you. Or if you work at least full-time, greater than or equal to 40 hours per week, or you do something else that is the equivalent of a full-time job, like care for a child, if any of that applies to you, let me know and I'll extend your due dates an extra 15 hours. So that'll be 8 a.m. in the morning. So you can either stay up late or wake up early and get the assignment in, and you deserve that extra time. Okay, so let me know. Contact me on Discord, let's say, if either of those apply to you, and I'll make sure to extend your due dates. Okay, but everybody else, 5 p.m. Okay, keep that in mind. All right, let's also talk about late submissions. I'm pretty lenient, to be honest. I will accept late readings on the textbook, labs, and check-in surveys up to the last day of instruction. So that's the Friday right before finals week. But the second it's late, I'm going to take half off. Okay, that's the give and take that there must be somewhere. So if you submit something late, I will accept it, but I'll only give you at most half credit. I'm knocking off at 50%. Okay, so you're welcome. And for the Zybook readings, for your textbook, if you do a reading assignment late, for some reason it doesn't transfer to Canvas properly, so just let me know, and I'll make sure to give you your half credit, okay? So let me know when you submit your Zybooks readings late. Everything else is automatic, all right? I do not you'll probably notice that I left it out. I don't allow late homework submissions because I'm going to release the answers to everybody, and that wouldn't be fair at that point. Okay, so that's late submissions. I'll also drop quite a few of your lowest scores for assignments. So I'll drop your lowest 3 homeworks, lowest 3 textbook readings, and then your lowest 2 labs. So like if you did very poorly on one, it's like it never happened. Okay, so that's what I'll do. I'll also be giving you all this stuff on Canvas on the modules page. Like I'll make this lecture 1 available to you. You'll click on that, and that's how you'll watch this video, right? So I'm going to give you all the slides and code that I write. It's all there. All right. Next comes the class server. I hope that you were able to get on that by now. Let me know if you're having any trouble. So I'll talk about that a bit more when I talk about the first lab. If you click on the lab, the video will probably be available by the time I give you this lecture. So yeah, you're going to turn in your programming assignments on our class server. I have a class server for us, and I made you all accounts. Please click on whatever the link was. I think it was SSH client, and that will tell you, I think I have a video there about how to connect to the class server and get stuff working. If you added the class late, you probably need a new account, and I can make you one of those if you tell me about it. Okay, so that's that. I'll show you that a bit more later in like the lab video, but we're going to be using that to do our lab assignments. And yeah, let's talk about the textbook real quick. So our textbook comes from a company called Zybooks. It's awesome, it's interactive, it's virtual, it's really, really cool, and I'm going to have you read it. Okay, so you have to buy it. Please get it and start the assignments. So the way you can get the book and the way you start your assignments is you go to one of the links. So like here's the chapter 1 link. You'll click it, and it will take you to the textbook. It'll take you to the start of that assignment. Here is the Zybooks website. So I guess it'll look like this for you, but like 1.1, that's the first section, and then it'll ask you some questions. They'll have some cute little animations. It's really, really nice, and it's wonderful. It'll really help you learn, so it's worth it. And you can see, if you go to the assignments tab, everything that I'm asking you to do for the assignment, and it should just automatically submit to Canvas every time you read it and click all the buttons and stuff. Okay, so that's your chapter 1 assignment worth 201 points, for example. Okay, so get started on that. Here are all the sections that I'm asking you to read and interact with, and that's how you get credit, by doing that interaction. Okay, so you can either buy it from the bookstore or directly from the Zybooks website. I think I would recommend the latter if you can, because for some reason I think like the bookstore makes you buy a physical access code, like they mail a physical access code to your house, and that just takes forever. So definitely buy it from the website if you can. Just click the first assignment, and if you don't have the book yet, it'll ask you to buy it before it shows you all this. Okay, but the way that you can see what to do is in this assignments tab. That shows you exactly what I'm asking you to work on. Okay, so all the assignments are up. Get started ahead of time if you're interested. That would save you some time later, I think. They're all here at the bottom. Okay, so that's that. That's our Zybook. Next we have Discord. Whee. So this is where I want you to go for Q&A, okay? Please ask questions in our Discord channel as much as humanly possible. Here's our Discord. When you click the link to add it, it'll take you to this page. Go to the welcome channel, scroll up to the tippy top, click the 100. You'll click the Fox to add the CSCI 26 channel, add your pronouns, and then so most of these will be available to you at that point. And then here is the CSCI 26 channel where you can interact with your peers. Okay, so please, if you can, ask your questions here. Ask them publicly so that your peers can help if it's like 3 a.m. and I'm not awake. The one thing you can't do publicly on Discord, where everyone can see it, is like post answers to stuff. So please don't do that. That is more of a message that's private. That should be a private message to me, a direct message, okay? So you can always privately ask me stuff with a direct message. I should be able to just like right-click my name and go to like message or something. I don't think I can message myself, but you get the idea. So yeah, that's me, and make sure to like change your name and all the stuff that I ask you to do. Like I want your nickname to include at least your last name so that I know who you are. Stuff like that. So just follow the rules and interact with your peers here. Everybody tends to enjoy the interaction on Discord, so I think it's a good place to be. And I strongly, strongly encourage you to contact me through Discord, okay? Don't send me emails, don't send me Canvas messages. There's a great possibility that it will take me a very long time to see them, and I might miss them otherwise, okay? So Discord, I can see notifications very, very easily. I think you can imagine what my email inbox looks like as a teacher, though. Okay, so that's why I encourage this, and that's why we have Discord. Okay, so please do that. That's Discord. Let's next talk about office hours. So you can see my schedule here. Excuse me. So Lawton's office hours, click. And you can click this link to join them. They'll be on Zoom as well as in person if you'd like to come to campus. So here, all these green things are when my office hours will be. I'll be on Zoom no matter what, but some of these also I have an in-person option if you'd like to come and talk with me there. Okay, so this is when I want my schedule to be. Come back here if it changes, and see if it changes before you attend, because there might be some meetings for the semester that I like have to be in, and I might have to move these because of them. So this is when I want to have my office hours, though. Hopefully it can all stay like that. But that's how you can look at them. That's how you can attend them. We're almost there, I promise. So last few things about logistics. So first, let's talk about asking for help and getting stuck. So this is a computer science class. I think you've noticed by now that like it takes a while to understand the material. You just have to like let it churn in your brain for a while, and that means you're going to get stuck a lot. I'm sure you've gotten stuck a lot by now. So when you get stuck for a long time, I want you to ask for help. Please, please, please. So let's pick a number. If you've been stuck for like half an hour on a problem and you can't figure out what to do next, please ask for help. Ask on Discord, send me a direct message, something like that. Come to office hours. I want to get you unstuck so that you can get stuck on the next thing, okay? There's no virtue in staring at your screen for 2 hours, and I know I used to do that. It's just not worth it. So please, please ask for help when you're stuck for at least 30 minutes. That being said, if you're stuck for 29 minutes, that's exactly the point of the course, right? So don't just keep asking questions once I help you a little bit. I want you to think for a little while longer. The 30-minute timer starts again once I help you, right? So that's the whole point, and that's how you learn. Okay, so that is computer science in a nutshell. Please ask for help when you get stuck, and I will get you unstuck. All right, so that is my promise to you. Almost done. So in addition to making you an account on the class server, I also have a class website, which is admittedly not very useful to you in this class. The one thing that it'll be great for is seeing your what do I want to say? Seeing your lab grades in a very pretty way. So this will be the one link you care about on the class website, but I made you accounts on this place called the class website, and it's a different place than the class server. Your username is the same, your default password is the same, but they are not at all linked. So once you change one password, it doesn't change the other password. So don't think anything different. So here's the class website. It's www.lawtonsclass.com. Your username and password right now are the same as they were the default for the class server. It's your last name all lowercase and an underscore and your student ID. So for example, this might be my username. Let me know if you can't log in. But once you go there, you will see not the admin stuff. That's just for me. You'll see all these things. And the one link that you care about in this class is going to be lab grades. It's going to be a very pretty way of looking at your lab grade submissions, okay? Because I'm going to have an auto-grader automatically grade your lab submissions the second you submit them, okay? So that's what you're going to be going there for, but try to log in and maybe change your password, okay? So your username and password are right now that thing. So this is your username and your password right now, okay? just like the class server. Please change it though. So yeah, I think we made it through all the logistics. Let's see how we're doing on time. Okay, so let's now actually talk about CSCI 26 stuff. Okay, please yell at me if any of this stuff above didn't make sense or I went through it too fast. I can definitely help you out with it more, but I didn't want to bore you for too long. Let's now actually talk about CSCI 26. So this class, its real name is Discrete Mathematics. So that's what we're going to be learning. It's a branch of math called Discrete Mathematics. And what that is, if you look it up on like Wikipedia or something, it's the study of mathematical structures that are countable or otherwise distinct and separable. So maybe you've like taken calculus or something and you've learned about like continuous functions that are all nice and smooth when you zoom in. We don't care about those in this class. What we care about more are discrete things that like have little chunks. So like here's how you can approximate a function discretely. It's like, oh, I take a little chunk at time 0, time 1, time 2, something like that. So this is what we like in a discrete mathematics class. That's the best that I can explain it in diagrammatic form. Obviously, you'll get more of a feel for it as we learn about stuff. But let's talk about some stuff that you already know that are discrete. So like trees, for example, are something that we will hit hard in this class and learn more about. They are a discrete structure because you can't like have 2.5 tree nodes. They're just, okay, you can have 2 or you can have 3, right? That's how it all works. That's discrete math. We'll learn a bunch of topics that fall under the discrete math umbrella. Some things you've learned before, some things you probably haven't, but it'll be fun nonetheless, okay? One cool thing that we'll learn about are like a more relaxed version of trees called graphs, where you can like have edges between all of these other nodes in weird ways and you can move around. So it's good for like modeling roads, for example, and finding like, all right, what's the quickest way to get from Clovis to Fresno, something like that. Okay, so we'll learn about those, for example, and all the stuff we know about trees will kind of apply. So that's discrete math in a nutshell. Let me also kind of like motivate to you why we're going to learn about all this stuff, especially logic and proofs. Those are going to be like the backbone of this class. So why in the world are we studying this? Logic, for example, if you define that, that's like the study of formal reasoning. Here's my example. I'm going to have you think about it. So here's an exercise for you. Please pause the video every time I give an exercise and actually do them. I promise it'll actually be helpful to you. But here's my exercise. What does it mean for a vector to be sorted? Please think about this. Like, all right, you got a vector. What's the definition of sortedness? Like, what does that mean? Pretend like I'm an alien. I've never heard the word sorted before. How would you define what it means to be sorted? And so the goal is to come up with a logical specification for a sorted vector to prove or to say once and for all what it means to be a sorted thing. Okay? I think you can imagine how useful that would be when you write a program. Because then everybody agrees on what it means to be sorted. And now we can discover algorithms for those things. Okay? So, I don't know. Think about that, come back, and let's talk about it. Assuming that you're back now. What does it mean for a vector to be sorted? 1, 5, 9, 42. That's a sorted vector, right? Maybe if I were you, here's what I would probably say. Like a sorted vector is, or something is sorted when like the values are increasing, right? So it looks something like this. It's not a sorted vector if it like ever goes down a little bit. So like v2, here's a non-sorted vector, 8, 6, 7, 5, 20. Right? The reason this is not sorted is because it's not increasing. Kind of like goes down, then up, then down, then up again. That's no fun. But I don't think that fully specifies things, right? If you say that something increases, that means it's sorted. Because this is also sorted, right? 1, here's a 4-element vector. 1, 1, 2, 3. That's also sorted, isn't it? So, how can you express that? Like, okay, it looks maybe more like it's a stair step idea. Like things get bigger or they stay the same. They're allowed to do that too. That's what it means to be sorted, isn't it? So here's how you can formally specify what it means to be sorted. So let's say, I don't know, let's talk about the indices of these vectors, because that's how you can relate things that are right next to each other. You can talk about adjacent indices. So this is how you would speak math, right? So let's say this. Let I and j be indices in V. Let's say that we're trying to say that a vector V is sorted. Vector V. Let I and j be indices in V. Let I be less than j. Okay, so like here's I, here's j. That's an example of I being less than j. Here could also be I, here could be j. As long as I comes before j, we're good. They can't be equal though. And what does it mean? Like I want to look at these now. Consider every possible I and j. If V is sorted, then the value of V at I is less than or equal to the value of V at j. This one's not sorted because it's not true there. This one is sorted because it is true there, right? So V is sorted, and I'll teach you what all these fancy terms mean and all these fancy arrows mean. V is sorted, you pronounce this if and only if. V is sorted if and only if V of I is less than or equal to V of j. And if this is true for every possible choice of I and j, then V is sorted, okay? And this is how you can like specify to a computer what it means to be sorted. And you can like talk about and try to come up with algorithms to actually sort things. That is my motivation for you. So if this is cool to you or interesting, you're gonna have a great time in the class, okay? So that's my motivation for logic to you. Let's also motivate proofs. Like why would you want to prove something? Let's bring it back to computer science. So let's pretend we have a really easy problem. We want to sum up all the numbers from 1 to n, right? So a very easy way to do it is to make something like this. So for example, let's say n is 5, and I want to sum all the numbers from 1 to 5. So like you'd have an iteration variable, you'd have some accumulator variable to keep everything in, and then you keep on adding into sum and I++ing as long as you're going from 1 to n, stuff like that. Technically, this function is actually incorrect, this idea. Do you see the error? Because if you wrote a proof, you'd be able to discover the error. Okay, so how do you know? Like this is what you're supposed to be computing, right? Adding 1 into sum, 2 into sum, 3 into sum, all the way to 5. How do you know for sure that the code you wrote actually works? That it does exactly what you're thinking? Right? How do we know that like right here, sum is equal to, if n is 5, sum is equal to 1 plus 2 plus 3 plus all the way, or just regardless of n. If n is 5, this is up to 5. How do you know that down here, after all these lines have completed, that sum is equal to this? Can you prove it? You actually can. It's really nice. So you can write a proof that guarantees that your code does the right thing. And actually the proof won't go through for this particular code because there's an error. Did you see the error? I'll show it to you in a second. So we'll actually discover it together. So here is a quick and dirty idea that I can teach you in just one slide. And we'll talk about it more when we get to actual proofs. But let's talk about preconditions and postconditions. So these are just ideas, things that are true before and after a piece of code runs. So a precondition is something that's true before a statement gets executed. And then a postcondition is something that's true after a statement gets executed. So let's like zoom in on this line. What's true before it's executed? What's true like right in between? Well, the variable sum is equal to 0, right? It holds the value 0. That's a precondition for this line. Does that make sense? A postcondition for this line is, well, I didn't touch sum on that line, so sum is still 0. And also, I made a new variable called I, and I set it to 1. So after this line, I exists, and it's equal to 1. Does that make sense? So that's a precondition and a postcondition for this line of code. If you'd like to prove something about loops, you have to come up with something new called an invariant, which is kind of like a pre and post condition combined in a sense. An invariant is something that's always true. Kind of comes from the word, right? It doesn't vary. So invariant is something that's always true, and a loop invariant is something that's always true about a loop no matter how many times it runs. So the reason we have to talk about loops in this way is like we might run the loop 0 times, 1 time, 2 times, we don't know. So if we want something to be true after the loop is finished always, we better have something that doesn't matter about, or that doesn't care about how many times we run that loop, okay? This is going to get a bit technical, but I promise it's worth it. So a loop invariant is something that's true after k executions of the loop, we say, for every possible k. After 0 executions, after 1 execution, after 2 executions. So here's the invariant. This is always true about sum and I, their relationship, no matter how many times this loop executes. All right? So for example, sum is always equal to, no matter how many times we run this loop, 1 plus 2 all the way to I minus 1. So I minus 1 is 0 here. So sum, this is saying that sum is 0 if we haven't run the loop yet, right? And that's true. Sum is 0 if I is 1. And it totally is before we run the loop at all. You see that? Isn't that cool? And this invariant is always true no matter how many times we run the loop. So let's pretend that the value of I is just I. Let's not pretend it's like 1 or 2 or 4 or something. So here's the idea. We're going to pretend that sum is equal to 1 plus 2 plus all the way to I minus 1. Pretend that's true, and let's run the loop. So let's say, like, yeah, I was less than n. Cool. What happens once we do that? How does sum change? Well, all right, sum becomes this. Sum becomes equal to 1 plus 2 plus dot 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 plus I minus 1. It was already that, right? And then we added I into it. Ooh, plus I. And then we also changed I to be 1 more than it was. What's I now? I equals I plus 1. Let's call this new I prime, all right? So I prime. And what is sum now? It's all the way up to, yeah, it's all the way up to I prime minus 1, if you look at it this way and squint. Does that make sense? That's the idea. This I is I prime minus 1. And so it still works, right? I is set to some value, and sum is equal to 1 plus 2 plus all the way up to 1 less than that value. Does that make sense? So it gets a little tricky, and I'd like to say more about this, but that's probably all that we have time for. But that's kind of what's going on, all right? And so that's why this is an invariant. No matter how many times you run this loop, that's true. So what happens when we're done? If we ever stop this loop, what's true about I? Well, I better be equal to, we know I is equal to n, because it was starting at 1, and n is like 5 or something. So it wasn't less than. If we stop the loop, that means it was equal to. It was equal to n. And because we ran this loop, and we have this invariant about how many times the loop runs, it's always true, what do we know about sum? Sum is equal to 1 plus 2 after this loop is completed, right? I is equal to n, so what does that mean sum is equal to? Sum is equal to 1 plus 2 plus dot 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 plus, not I minus 1, because I is n. That's n minus 1. Ooh, and there's the problem. This loop doesn't execute enough times. It doesn't go all the way to n, right? If n is 5, this goes only to 4. Did you catch that? Ooh, so we would like this to stop not when I is n, but when I is n plus 1. Because then we'd have sum equal to all the way to n. And the way we fix that, of course, is to say while I is less than or equal to n. You see that? And taken together, all these invariants and things, you can prove, and we kind of just did, that it works, and sum is holding the value that you thought it should hold at the end. Okay? I'd be happy to explain this in more detail later. Maybe this was a bit weird sounding over here, but if you think about it long enough, it really does work out, and the logic is there. So that's why you might want to care about proofs a little bit, because you can prove that your code works, and that it always will work. Isn't that nice? So hopefully you can see how this is going to make you a better computer scientist. It's not really, we're not just throwing math at you for no reason. All right. It might seem like it's very abstract and weird, but you can always bring it back to the code if you really need to. Okay. So that is kind of what CSCI 26 is about. And yeah, let's keep on trucking. We're getting through it. Okay. So I have a lot of real things to talk to you about today, and we have to get there. Okay. So first of all, I want to teach you about a new programming language. It's called Racket. Maybe you've heard of it before if you've taken my CSCI 1 class, but you're definitely not required to. You are required to write C++ in this class just for reasons that the school has said so. I'm not required to write any C++ in this class, so I'm going to write a language. I'm going to use a language called Racket. Okay, it's what's called a functional language. It's really, really cool. And it's a dialect of the language called Scheme, which used to be very popular as like a first language to be taught at like a very fancy school. Like MIT used to teach Scheme as the first language. Scheme is itself a dialect of a language called Lisp, which is one of the first programming languages ever. Lisp stands for List Processing. I'm never going to test you on Racket. I'm just here to poison your mind with it. So you're just going to learn it as you watch me do it, okay? There is a tutorial that I gave you. Please read it if you're interested. But Racket is a functional language, and it's based around lists of things. So things look a bit weird. The syntax looks a bit weird. So like instead of calling a function like this, foo of bar and 42, in the Racket language, you write it like this. You write a parenthesis, the name of the function, and then the arguments are space separated, foo bar 42. That's what the syntax looks like in Racket, okay? And this is like a list of stuff at the same time. So that's why it traces itself back to there. In Racket, you can write parentheses, square brackets, curly braces, and they all stand for the same thing. They all stand for these things. So I could have written this as angle brackets this instead of curvy brackets that, and it would have run the function still. Okay, so yeah, let me show you Racket. I don't think there's enough time for me to type it, so I just brought it in and I made it ahead of time. But here is the hello world file. Racket files are .rkt usually, and the very first line of a Racket program, because the Racket language is like a bunch of languages in one, you got to tell it which one you're trying to use. The default, or the original language, is just called Racket. So you say lang Racket, kind of like include the language or something. It's like your IO stream. And then here is your one-liner. There's no main function in Racket. It just starts running the code kind of like Python, and this is a function call. We're calling the display line function, and we're giving it the string, hello world. Okay, so if we run this, it will display the string hello world. And then comments in Racket start with a semicolon, but usually people use 2 semicolons, as you would use like 2 slashes. But a single line comment in Racket is just, you can start it with a semicolon. Everything after that is the comment, but people like to double up for some reason. And so here is how you can run it. Racket it can be an interpreted language, so you just give it the name of the file. There's no compilation, it just runs that file. And so here it is, printing hello world. It's so weird, right? This is a function call. It looks a bit odd, but that's how it works. Let's next talk about just a bunch of stuff. So definitely read the tutorial if you're interested, but here is how you can do some interesting stuff in Racket. So first of all, again, there's no main function. You can just start writing code, and it runs that code. Oops. So yeah, here are a few lines, and we'll talk about them all. So define is how you create a variable or a function. So here's a variable called pi, and I'm defining it to be 3.14. It's just parentheses all day long in Racket. All right, and so here is how you define a function. You just pretend that you're calling it, kind of. And we're making a function called print from 1 to, and then the argument is going to be called n. This is the parameter name n. And then here's an if statement. It's called cond, and it's just a bunch of parentheses. So first of all, the first tip for you that I have about Racket is, first of all these things are interchangeable. Like this could have been a normal parenthesis. it's just customarily done like this. It could have been like that. This is just the customary way of writing Racket code, just to make it a bit easier on the eyes. But white space doesn't matter in Racket, first of all. Like, it could have been all this. And so my hint to you is, if you're reading somebody who's actually good in their code, they will have indented in a nice, pretty way. So don't like worry about looking for all the parentheses when you're reading a Racket program. Look for instead the indentation. Okay, because that will make it like forget about the parentheses, just pretend they weren't there. And then this should be easier to read if you just don't look at the parentheses and the square brackets. Okay, so here's how you print from 1 to n. It's a recursive function. So base case, you're trying to print from 1 to 1, so n is equal to 1, then print 1. That's how you print from 1 to 1. You're done. Otherwise, if you need to print from 1 to n and n is not 1, we have a recursive case. So first of all, recursively print from 1 to n minus 1, because that has to appear first. That's like your 1 to 4, and then you print your 5 at the end. Okay? That is how you can define a function, and that's a recursive function. So it'll print from 1 to 5, just like that. Okay? So let me run this down here so you can see it. Racket, cool stuff. So here it is printing from 1 to 5. Beautiful. All right. Next thing, you can define structs just like you can define them in C++. So here is a struct. It's called 2D point, and 2D points can hold x and y coordinates, right? So this is how you define a struct. It makes a few things. It makes a constructor, and it makes some destructors too. Destructor in the sense that like you can get stuff out. Like you can get the x out, you can get the y out. It makes a bunch of functions though. This is a functional language. Alright, so just watch it all work, and I promise it'll start making sense. So here's how I can make a point. I can use my struct like a function, and it creates that structure. It makes 5 and 7 come together to be a 2D point. Alright, so here's P. It's a point 5, 7. X is 5, Y is 7. Then I can print it out. I can print pieces of it out if I'd like. So display the x coordinate, 2D point x. You can use dashes in code in Racket in a variable name. That's totally fine. So display 2D points x of P. And so that's go into P, find the x coordinate, print that out. That's the 5. Okay? Here's how you make lists in Racket. Lists are very important. So you just say list, call it like a function, and it makes a list. All right, so here's L1. It's the list holding 1, then 2, then 3. All right? Shorthand for that is you just use a quote before the actual list. Otherwise, it thinks it's like a function call, like you're calling the one function or something. So this is a list L2, and you can, either one is interchangeable. Either syntax is fine. And so here's me printing L1. It's printing 1, 2, 3. All right? A cute feature of functional languages is that you can start applying functions. You can start passing functions to functions. Have you used lambdas in C++ before, maybe? Go and look those up if you haven't seen them before, but this is like the cute quick version of everything. So here's me making a function called add2, like it just adds 2 to whatever you give it. There's no return in Racket, it just implicitly gives back this final thing. So this is a function that takes something, n, and returns back that thing plus 2, it adds 2. Here is what you can do. A function called map is used to apply a function to every element of a list. So here's the map function. It takes a function, and then it takes a list. So we're mapping add2 over L1, and L1 was 1, 2, 3, and it creates a new list. If we're mapping add2 to every element, like it's calling add2 on 1, add2 on 2, add2 on 3, making 3, 4, 5. Do you see that? Does that make any sense? So that's what map is all about. It's applying a function to every element of a list. It's really cool, and that leads to some very powerful techniques. Okay, it's kind of silly to make an add2 function if we're just going to use it once. So let's make a function inside the map call that just doesn't have a name. Right? So that's called a lambda. A lambda is an anonymous function. It's a function without a name, and here it is. Here's the equivalent of add2, just it's not called add2 anymore. So map this function. It's a function that takes some variable, call it x, and gives back x plus 2. So map that function that takes something and gives back itself plus 2 over L1. And again, it does the same thing. Do you see how that might be quicker? That's what lambda means. Make a function on the fly, in line. Isn't that cute? And then finally, in the same vein, there's a function called filter that extracts only the elements of a list for which something returns true. True in Racket is number sign T. False is number sign F. So here is filter. Filter, here's a function. Do it on L2, which is still 1, 2, 3, right? Filter only the elements of L2 for which this returns true, right? So take the element and test if x is greater than 1. Do you see how I'm reading that? It's a bit backwards. The function always goes first, so like plus, this is x plus 2. This is x greater than 1? See that? It's a little weird, but you'll get used to it. So yeah. Is x greater than 1 for the one element? No, so it's going to skip that one. How about 2 and 3? Yeah, it's going to keep those. So it's filtering only the things that are true when you apply this. And that's the 2 and the 3. Okay, so there's plenty. I could talk about this all day. It's a really fun idea, functional programming, and I'm a big fan of it. But if you study this, this is a great start, I would say. Okay, so that's a Racket. It looks a little weird. I'm not going to ever test you on it, but I promise it is worth your time. Okay? Those are my examples for us. All right? And now I'm actually ready to talk about required content. Okay? So let me go and pull all that up. I will use the magic of video editing to make it all look seamless for you, but I'll be right back. Okay, welcome to the actual first set of real slides for the class. And I'm going to get through just a few of them today, and then we'll stop. But I want to talk about logic. That's our first real topic. And so I'm having you read the logic chapter of the book, and I'm asking you to start some logic homework. All right, so I'll give you your 0th homework now. It won't be due for a while. Remember that as long as you try and you get at least 70%, I'm giving you full credit. So please make an effort, ask me questions about it. But here's your homework 0. You'll click it. Obviously, I'm going to get rid of the answers. This link should be dead anyway, but you're going to submit a PDF with your answers, and then after the due date, I'll give you the answers, okay? But here is the homework file. Let us go to it. And so here's the idea. Here, you can print this out, like write on it, scan it back, submit it, or you can like download a PDF editor if you want to and change it there. But here is your homework. You'll just be answering all those questions. Okay, so that's that. Let's talk about logic now. So the first thing that I want to talk about is propositions. It's a fancy term. It's our first fancy term. And then logical operations, which you already know a few of, actually. And we'll start studying it formally, though. Okay? Let's talk about them. So first of all, propositions. A proposition, this is just fancy, flowery words. You'll get used to it as we go through the class. But a proposition, it's a statement, so like a sentence, that is either true or false. Okay? A statement that is either true or false. We'll get to some examples in a second. But true can be written a million different ways in computer science, right? True can be written, or in discrete math, can be written as T, if I don't want to spell it out. It can look like something that is almost T, but not really. It's like a upside down wedge kind of thing. So it could look like that. True in computer science, like inside of a computer, could be a 1, right? It could be the word yes. Yes means truth, right? It could be high voltage if you're an electrical engineer. That's what true means, right? True could be any of those things. False, falsehood, you can write it like any of these, right? Could be F. Could be the T turned 180 degrees. You won't see this until grad school, probably, but I promise it's used. Could be a 0. Could be the word no, right? False, not true. Could be low voltage if you're creating a circuit. There's plenty of different other things too, but that's the idea. Proposition is just something that can be true or false, right? Like the sentence, today is Saturday. Maybe when you're watching the video, it's a false proposition, but when I'm recording it, it is a true proposition for me. Okay, so that's what it is. It's just a statement that's either true or false. You can have words, you can have sentences that are not a proposition that's neither true nor false. I think your book gives you an example, but I can give you one in office hours if you're interested. So That's a proposition. And then we have logical operations that you can perform on propositions. You can combine them with certain rules, okay? So for example, like I can make a logical operation. I can define a happy face operation to work like this. Like if you give me true and false, if true is on the left side and false is on the right, in between the happy face operator creates true, like it outputs true, for example, right? And then if you want this to be like well defined, you have to define what happy face means for two falses, for two trues, right? You can make this a legitimate operator if you give every option, right? You say, what does this do for all these? Maybe it's always true, like happy face means yes. The answer is always true. Something like that, okay? But that's the idea. That is how you can define any logical operation. You have these four options if it takes two things, and you just say what is the output, okay? So you know a few of these already, don't you? You know and. You've used and like this, right? Two ampersands in C++. You can combine propositions like that, right? So here are two propositions. Like technically it's, I don't know. Let me write it like this. I like squirrels. Yeah, this is two propositions. I like cats. That's the true or false statement, right? I like squirrels. That's another proposition. Yeah, I can combine those with an and. Does that make sense? You can give variables to propositions, so you can like write things out. Like you can say, okay, P is I like cats. Q is I like squirrels. Then I can combine them by saying P and Q. In math, we don't say two ampersands. That's just C++. In math, we say this little wedge symbol. Okay, that's what and is for us. So we can say P and Q. P and Q. That's how you express this idea. If you've defined P to be I like cats and Q to be I like squirrels, this is now representing the idea that I like cats and I like squirrels. Does that make sense? It's like two things at once. If you give a logical operation, you have to define how it works, right? If you give me true and true, what does it mean to and those together? If you give me true and false, what does that mean to and those together? You remember all this? So a truth table is how you display that. That's one way of doing it, at least. It's one way of defining how it works. So it's the truth value of a compound proposition for every possible combination of truth values for the variables contained in the compound proposition. So that's flowery math speech, and I promise you will eventually get used to it. Yeah, so that you give me P and Q. Here's what P and Q means. Here's I define the output, right? And remember that when it's and, the only way to make a true when you're anding stuff together is when they're both true. If there's a false any other way, the answer is false. Does that make sense? So here I am anding P and Q. The only way to make true is for them both to be true. Okay, that's it. So the symbol for logical and is this little wedge-shaped thing. One way to memorize that is that like it's a capital A, but without that little dash in between, right? It's like get rid of that part. That's your and symbol. All right. Another word for and in mathematics is called conjunction. It's combining things in a certain way. It's joining them, conjoining them. So conjunction. That's another word for and. All right. And there's only one way to make it true. Right. P and Q better both be true. Okay. Hopefully that's coming back to you. That's and. You know it. But we're just getting mathy with it. Next we have or. You've used this or before. This is your double pipes. There's actually two different kinds of or, first of all. Maybe you've not heard of the other one. This one's called inclusive or. Okay? The symbol for it is this little V-like thing. This is the or that you know from programming, though. All right? So you take P and Q. P ORed with Q looks like this, right? If you give true and true, if you OR those together, you get true, right? The only way to make false is when they're both false. Like, or is just given back true if any of them are true, right? That's the idea. So here's an example of using the or operator. You can take this class if you took CSCI 41 here, or if you took an equivalent data structures class somewhere else, because that's like a prereq. So this is a statement that you can define in math using the or operator. You can take this class if this is true, you took CSCI 41 at Clovis, or if you took it somewhere else. Maybe you took it at Fresno State. It's also okay if you did both. Like you really wanted CSCI 41 content, so you took it at Clovis, you took it at Fresno State. You can still take this class, right? That's what that's saying. And so the symbol for or is that it's like a V looking thing, but it's not a V at the same time. And here's my little mnemonic for you to remember it. It's like, I don't know, think of it as like a vortex. It's swirling together all the things, and it's picking out the true whenever it can. The word that's fancy and mathy for or is called disjunction. So and is conjunction, or is disjunction. There's a cute, like, fancy duality going on in that there's only one way to make and true, and there's only one way to make or false. Isn't that kind of interesting? The only way to make it false is if they're both false, right? So that's or. I'm pretty sure you remember all this, right? You've used the or operator plenty of times, but maybe you haven't seen this table since like CSCI 40 or something. So that's inclusive or. There's actually another kind of or. There is an exclusive or, okay? There's an exclusive or. And so let me say, like, let me underline these things. Like, this is true if you did this, or if you did this. You took an equivalent data structures class somewhere else. So I'm oring together those things, and it's also okay if you did both, okay? The exclusive or is making the is differentiating between did you do both or not, okay? This is an or that you use in real life. You don't really use it a lot in computer science until fancier classes. So for example, like the waiter, you're at a restaurant, and the waiter says, super salad comes free with your entree, right? So it's implied, right, that you're not getting both, right? You'd have to pay extra money. This kind of or, this or from real life, is kind of saying you get one or the other, not both. Does that make sense? So this is exclusive or. Sometimes say called XOR for short. The symbol is this little circle with a plus in it. But here's the truth table for exclusive or. So if you P, X, or Q, here is what you get. It works the same for these bottom three. Like, all right, if this one's true and that one's false, exclusive or is true. If that one's false, P is false, but Q is true. If you XOR them together, you get true still. If none of them are true, then again, you had neither. You're not getting anything. You're getting false. The one place where it differs is in this case. If they're both true, the exclusive or of two trues is false. You see that? That is the idea. So it's like they tilted the X, made it a plus, put it inside of an O, exclusive or kind of thing. All right? And that's how you can represent this idea, soup or salad. You're not getting both. You're not getting soup and salad, right? That's false. But you can have soup and no salad. That's fine. You could have salad and no soup. That's cool. You can't have neither, though, because that would defeat the purpose of buying this entree. That's also false. Okay? So that's the idea. That's like exclusive or. The more you use these, like I'm forcing you to use all this in your homework, it'll eventually make sense. Okay? And please yell at me about it on Discord or in office hours, and I'd be happy to talk to you more about all this stuff. But we're just setting the groundwork, right? Just all these symbols, you have to see them so that you can use them. All right, next comes negation. Negation is your not. It's your exclamation point from C++. The symbol for negation is this weird looking thing. It looks like that. I like to think of it as like a diving board. It's flipping things. That's the idea. So let's just go into the example. So like you can negate, right? The negation of the proposition I ate breakfast is I did not eat breakfast. Does that make sense? It's like it's making true false and false true. That's what negation means. Also called not. Logical negation. It's flipping between true and false. So you give me true, not true becomes false, right? You give me false, not false is true. The negation of it, okay? And so the symbol looks like this. I think of it as like a diving board that somebody is like about to do a flip on. It's like flipping false to true. That's the way that you can memorize it if you want, okay? That's negation. It's very easy. It's a simple one because it only takes one thing. Like all these other ones were like combining two. This one just takes one thing and it flips it. That's negation. And yeah, I'd like to ask you a question about that before we go, but this will be the last slide for this class. So here's my silly thing. If you've never taken a class with me before, I like to try to be fun and whimsical. So we're about to have our first in-class exercise where I really want you to pause and think about CSCI 26 content. So you can abbreviate in-class exercise as ICE, and our mascot here at Clovis is the Crush, which is some sort of bowl. I don't know why we called it the Crush, but that's okay. So naturally, we're going to call our in-class exercises crushed ices. So here is your first crushed ice. Please pause the video. It really, really helps if you do these. I promise, if you take the time, you'll learn a lot more than just breezing through these and watching me do give the answer. Okay? So here's what I want you to do. Express each of these statements down here in logic using these combiners, these operators that we've learned, using the following variable, so you don't have to write things out. So just use P to mean I've taken CSCI 41, and use Q to mean I've taken CSCI 45. Okay, so represent these ideas using P and Q and these logical operators, and, or, negation, exclusive or, stuff like that. So, all right, let's try. You can try all of them, but I'll give you some time to pause, and I'll talk about them first. So, represent I have not taken CSCI 41 using P and Q and our logical operators. All right, so hopefully you paused the video, you pondered that idea. So that's like, well, it's almost P, right? It's just the negation of it. You see that? So P is saying, you just declare P, that's saying I've taken CSCI 45, but I'm declaring that the opposite's true, right? I'm declaring that P is false, not P is true, right? I haven't taken CSCI 41. Do you see how you can do that? That's how that works, all right? What about B? I've taken CSCI 41, but not CSCI 45. This is interesting. Like, I've told you, like, and or and not. What is but? All right, you have to really think about that. So, I've taken CSCI 41, but not CSCI 45. Here's the answer. Well, it's saying, all right, P, yeah, that's true, right? I've taken CSCI 41. What about 45? I've not taken CSCI 45. It's not true, right? It's not going to be or here. That would be like, I have taken CSCI 41, or I have not taken CSCI 45. There's a different feel to that. But secretly translates to and. Because both of these are statements, right? These are things that I am saying are true at the same time. P is true. I've taken CSCI 41. I'm saying that that's true. And then I'm also saying that not Q is true. I'm saying that I have not taken CSCI 45. So but translates to and. Okay? Your book will talk a bit more about that. All right, what about this one? I've taken CSCI 41 or CSCI 45, but not both. Just one or the other, which would have some weird rules if the college would get really mad at you, but apparently, let's pretend that's possible. So I've taken CSCI 41 or CSCI 45, but not both. And first try it if you're allowed to use XOR, and then try it if you're not allowed to use XOR. Okay, you got to use something else. So if exclusive OR is allowed, this is pretty easy. Like, I've taken CSCI 41 or 45, but not both. Well, I can just put them together with an exclusive OR, because this is claiming, like, I'm in one of these cases, right? Either I've taken 41 but not 45, or I've taken 45 but not 41. And that is exactly what exclusive OR is claiming. Like, you're in one of these states, not any of these. Okay? So if exclusive OR is allowed, P XOR Q is one way to claim this, one way to express it. So I've taken CSCI 41, exclusive ORed with I've taken CSCI 45. That's representing the fact that I've taken CSCI 41 or 45, but not both. Okay, if you're not allowed to use exclusive OR, this gets a bit more complicated, but here's how you can think about it. So OR comes into play, right? It's one state or another, right? Either I've taken 41 and not 45, or I've taken 45 and not 41, right? That's what it means to have not both, to have not completed both. So I'm either in the state where I've taken 41 and not 45, or I'm in the state where I've not taken 41 and I have taken 45. Do you see that? That is how it works. So here's your ands, here's your ors, here's your nots. And because these are claiming the same idea, these are actually equivalent statements. You don't need exclusive OR. This is using, like, it's a bit more roundabout way of saying the same thing, but it is saying the same thing. It's equivalent, logically equivalent. I'll use 3 instead of an equal sign. I use 3 lines. That means logical equivalence. Okay, so that is how you do it. All right, so that is how you can express these statements. Please read your book, start your homework, and it'll make a bit more sense when you do that, and yell at me if you have any questions. But that does bring us to the end of our very first lecture together. So thank you for watching, and I'll see you in the next one.